Hi, everyone. Today, I'm going to talk about our recent work with Saga Patel and Sangeeta Abdul about explainability of reinforcement learning agents in for systems applications. Saga did internship with us over the summer, and this basically results of his internship. So recently, we see a lot of papers that show success of reinforcement learning agent in governing different system tasks. So examples of such applications are adaptive video streaming, NSDN network optimization, cluster job scheduling. And in all these papers, it has been shown that if you replace some maybe manually designed or what traditionally used heuristics for certain processes with reinforcement learning agent, then you will see significant improvement. In fact, at VMware, we also see the same kind of a trend. There are a lot of manually designed heuristics that are kind of hard-coded and now very hard to parse. And there was a push that if we also don't understand what's going on there, maybe we should try reinforcement learning and see whether we can get a good agent to replace this manually designed heuristics. However, when it comes to real deployment, it's often there is a need from the user to understand what this controller is doing, because controller is a black box, right? It's a neural network. And with all people concerns about what the neural networks are doing, it's good to provide the user with some means or some tools that they can play with these controllers and try to understand what is going on. And it also build up trust on the user side to trust your control, that it does some sensible things. So a quick background, we are working with a standard reinforcement learning loop. When we have an agent that follows some policy, it takes observation as an input to produce an action. This action goes into environment, and the environment taking observation and action moves to the next state of the system and also produces a reward. So as I mentioned before, we kind of targeting systems applications, and as our running example, we'll be using adaptive bitrate streaming problem. It's a very simple problem. You have a server and you have a client, and server streams videos to the client. The video is streamed in chunks. Yeah, visualization of it. So you every time point you have to send one chunk of the video. But also, depending on the network conditions, you can send this video on a different quality. So you might have like a low quality video, medium quality video, maybe high quality video. So at each time point, you have to decide what kind of quality you use for the next chunk. So how this problem is kind of mapping to the standard loop. So our observations will be history of the network, how network behaves and how video player behaves. Our action, so action of the controller is to pick what quality of the video chunk will be next. And environment, when we give a state and our decision, it outputs a reward, and reward in this case captures how user perceive the next, like how good the experience of the user in watching this video. It's a composed reward. I'll talk about it later, but overall it capture quality of the experience. Right. Okay, so now I'll talk about two special properties that at least we've identified in systems applications that are somewhat different from standard reinforcement learning loop. First of all, we don't have a model of the environment. What we have is traces. Traces, usually it's a real world traces that actually capture uncertainty of the environment. So here are some examples to make it more clear. For example, in adaptive bitrate control problem, trace would represent throughput over time, right? So and throughput actually for this application capture external condition, capture uncertainty. In other applications, it can be resource demand over time, load over time, or incoming jobs over time. So this is a traces that we are given, and usually they are publicly available. And what environment is doing, it just replaces traces, right? So we don't have any model, we have these traces recorded somewhere on real clusters, so on a real streaming platform, and we just replay. Environment just replaces traces, and this is how the environment is modeled. And traces are actually quite tricky, like in the case of throughput, you have favorable, like very good network conditions, you have bad network conditions, so the traces distribution varies a lot. Another special property that we will be using is regarding the reward function. So in these applications, reward function capture quality of the experience, or how well the system performs. And usually it's designed by the designer who has very good understanding of the domain knowledge. So it means that a reward is usually a linear combination of some important performance characteristics of your system. In case of adaptive bitrate, for example, we have a linear combination of three performance characteristics. Quality of the video, so you want to send, it's a positive contribution or kind of a positive reward because you want as high quality as better for the client. You don't want to see a lot of policy change. You don't want to see that client gets one chunk of the video very high quality, then very low quality, it jumps all the time, so it's not a very good experience. And the worst thing that can happen, at least in these settings, it's stalling when no video to play. The client just has interrupted experience, so you really don't want it to, you penalize. And similar composed reward you can see in other applications like congestion control and age caching. Right, to summarize, there are these two properties that we'll be exploiting for our explainability results, so that we have these traces, and importantly that they're publicly available, so you can always have access to them. And we will also exploit that the reward functions are decomposable, and each component of the reward function is meaningful. Right, so to convince you that there are these publicly available traces, for example, for adaptive bitrate control, you can go to this platform. It's called Puffer. It's run by Stanford for streaming videos to clients, and there there are tons of traces, tons of data. You can go there and just collect it. That's what we did, for example. And you can even train your controller and run there and see how it performs. So it's a live system. Every day it collects traces. They're publicly available, so anyone can go and try. Right, so now we'll talk about explainability. So explainability, as I said, it's originated with our discussion with various product groups that we do need some form of explainability. But before we even start working explainability, is a tough question: what is explainability? How we are going to explain? What is the unit of explanation? On top of it, there are multiple assumptions that you have to make. Like, do you know the model? Is it a black box? It's a white box. So we did have to do multiple decisions. So we decided that we'll be working in black box settings. So we don't know internals of the policy. For us, it's a black box network. So we are going to the black box settings. And what we are going to explain, we want to explain the action. We want to explain why at current state was controller decides to take action. Certain action, A or B. Now, the next question is how we are going to explain it, right? What is the unit of explanation? What do we give the user as an explanation? Again, there are multiple things here. You can explain the action looking at the current state, but we decided to do a different thing. We decided to do the explanation by looking at the future. So conceptually, we want to give the user understanding, oh, what if you take action A, what are the future consequences? Or if you take action B, what is the future consequences? In this way, first of all, we provide the user with some understanding, what's going on, what is the consequences of taking certain actions. And if you have two actions, you can actually compare and kind of see why action was better than the other. So how it will look like, oh wait. Right, so how it will look like, let's say we will have our explainer, and we have one action given the same state. We have two actions. Either we send a low quality video or high quality video. An explainer will kind of summarize future consequences of this action. So what are the future consequences of sending low quality chunk or future consequences of sending high quality chunk? 5 minutes, yes, it's fine. Our key ideas is the following. To give a user explanation, we summarize future in our decomposed reward components. Remember that I was emphasizing that each reward component has a meaning. So what we will give as a user, we will give a expectation how each reward component will evolve when they take a certain action. And for that, we need to obtain these quantities, we need to learn a predictor, right? That given a state in the action, it outputs what is the expected value for this reward components over time, looking into the future. So how we do it? Remember that I said that we assume that traces are publicly available, so somewhere we can get them. We have no assumptions on the controller, so it's a black box for us. Now, to build the explainer, our first step is to transfer the problem of building explainability to supervised learning problem. So we take these traces and we take a controller, which is a black box, and we run it, and we collect data. So given a state in the action, we collect the rewards over a certain period of time, but not just a reward, but remember this decomposed reward. So reward component for the quality, for quality change, and for the stalling. We collect it a certain over a period of time and we weight them. So for each state in the action, we collect this quantity. It's expected return for the quality, expected return for the quality change, and expected return for the stalling. And now we have a supervised learning problem, right? So we run this policy and environment quite a while, and now we have just a data set, observation or state, action, and what are the future consequences of this action. And we just have a data set. And then from that, we can learn a predictor. So it's just a supervised learning problem. We train a neural network, which has quite complicated architecture, but anyway, at the end, it's just a neural network. And this is our explainer. So now, few important properties, at least we like about our explainer. So we don't, all the previous work, not all, but many papers that were looking at similar type of questions, they were altering the training loop. So they were interfering the training procedure. So we don't have any knowledge of the training procedure. We don't care what it was. We just have a controller to work with. We don't have any assumptions about the policy because we just core it, right? And our cost for the explanation is very low because it's just a neural network again. So you will give me your state, your action, and I will give you consequences of this action. Right, so this is how it will look for the user, at least in the basic form. Again, we have our explainer now. We will learn it. We have two actions: low quality video, high quality video, and what we will return to the user expected or returns for each of the components of the reward function. So how we expect quality will evolve over certain bounded horizon, of course, how quality change will evolve over bounded horizon, and how stalling. And we do it for both actions, and then just visually, user might be able to compare and make sense of it. Of course, there are questions like how to make sense of it, but even with these simple settings, it's already in some cases, yeah, I'm almost done. Right, so I'll show the results. We run it on two systems, adaptive bitrate that I was using as a running example, and congestion control. Just to give you an example, let's say we have this adaptive control system and we have two actions, A and B, right? And maybe you unexpectedly for you, controller drops the quality of the video, and you're wondering why the controller will drop the quality of the video. Should we send the high quality video because it's better for us? And what our explainer returns, it says, okay, if you take action A, you have some quality video will be just numbers, right? So you will pay for the quality change, you have a drop on the quality video, but you will have no stalling. But if you keep sending, let's say, action B is a high quality video, then if you keep sending in the high quality chunk, then you will experience stalling that has a highest penalty. So you really don't want it. Yeah, okay, so just we showed that for then what's important to estimate this numbers correctly, and we show that we do it better than baseline. And yeah, so this in summary, we propose this framework for explainability of reinforcement learning controls, where we are targeting systems applications, and we use this 2 examples, adaptive bit rate and congestion control. And the future work is to see whether we can apply to other systems. That's it. I think the end of my talk. Thank you.
Quick question while the next speaker gets, you can set up.
Thank you for the great talk. I was wondering what exactly goes into your observations of the state? Like, are you sort of considering also the historical demand you've seen as far from choices?
So it actually depends on the controller. In many of them, yeah, you still have a bounded history, like but it depends. It can be throughput, previous throughput, and current throughput, latency, buffer size for the adaptive. Some historical information, but we are trying to.
Okay, thank you.
All right, our next speaker is Nitin Sharma from PayPal, whose title is Generating Adversarial Examples and Defense Methods for Online Fraud Detection.